Good morning. My name is Héctor Vargas Rodriguez from the University of Guadalajara, and today I will present our work on exploring stability in a diffusive typhoid fever model with protection strategies. Thank you for being here. Let me give you a brief overview of the talk. First, I will motivate the problem and describe why typhoid fever still demands mathematical attention. Then I will present the model formulation, including the transition from an ODE system to a reaction diffusion PDE system. After that, I will discuss the qualitative analysis, equilibria, the basic reproductive number, positivity, and boundedness. We will then look at the stability regions under diffusion, followed by the numerical scheme and its properties. I will close with the numerical results and conclusions. Typhoid fever is caused by Salmonella enterica, TIFI, transmitted through the fecal-oral route, essentially through contaminated food and water. Despite being preventable, it remains a major public health burden, approximately 16 million cases and over 6,000 deaths every year, concentrated in low-income countries with poor sanitation. The complications can be devastating: intestinal perforation, internal bleeding, myocarditis, and meningitis, with children and pregnant women being especially vulnerable. Our goal in this work is to develop a special temporal mathematical model that goes beyond the classical well-mixed approach by incorporating spatial diffusion and to use it to evaluate protection strategies such as vaccination and treatment. Let me highlight the 5 main contributions of these works. First, we formulate a reaction diffusion model with 4 compartments: susceptible, infected, protected, and treated, what we call the ICE-APT model. Second, we rigorously prove that the continuous model preserves positivity and boundedness, essential properties from a biological standpoint. Third, we analyze stability regions for both the disease-free and endemic equilibria, examining how diffusion coefficients and other parameters affect them. Fourth, we develop an implicit finite difference scheme and prove that it is unconditionally stable via von Neumann analysis consistent of order h² plus tau and positivity preserving using M-matrix theory. And fifth, we validate everything through numerical simulations. Here you can see the compartmental structure of our model. The population is divided into 4 classes. Individuals enter the system either into the protected class P at the rate alpha times lambda. Think of this as vaccinated newborns or individuals receiving some form of prophylaxis, or into the susceptible class S at this rate. Protected individuals can lose their protection and become susceptible at the rate gamma. Then susceptible individuals become infected through the force of the infection lambda, which depend on the contact rate, the probability of transmission, and the effectiveness of protection. Infected individuals receive treatment at the rate beta and move to the treated class T. We assume that treated individuals do not get reinfected. All classes experimental natural death at the rate mu, and the infected class has additional disease-induced death rate delta. The table below summarizes each parameter. The base model is a system of four ordinary differential equations, what you see at the top. This is the model studied by Nithiri in 2016. It assumed a well-mixed population with no spatial structure. Our contribution starts here. We introduce spatial diffusion by adding Laplacian term with diffusion coefficients for each compartment. The domain is bounded, is a bounded region omega with a smooth boundary, and we impose homogeneous Newman boundary conditions, meaning zero flux at the boundary, so the population cannot leave the domain. This transforms the system into a set of reaction diffusion partial differential equations. The diffusion term captures the spatial movement of individuals, for example, how infected people move between neighborhoods or how contaminated water sources shift geographically. This added realism is precisely what motivates the entire study. A central quantity in any epidemiological model is the basic reproductive number R0. We compute it using the next generation matrix approach. The result is this expression, where bar theta is the effectiveness of the protection, theta is the infection rate contact, P is the probability of catching typhoid fever, beta is the treatment rate, mu is the natural death rate, and delta is the disease death rate. The interpretation is intuitive. If R0 is less than 1, each infected individual generates on average less than one secondary infection. So the disease eventually dies out and the disease-free equilibrium is achieved. If R0 is greater than 1, the infection sustains itself and the system converges to the endemic equilibrium. Notice that increasing the protection effectiveness bar theta or the treatment rate beta directly reduce R0. This is the mathematical confirmation that vaccination and treatment are effective control strategies. We identify two equilibrium points by setting all time derivatives and diffusion terms to 0. The disease-free equilibrium, EDF, has 0 infected and 0 treated individuals. The susceptible and protected populations settle at levels determined by the recruitment rate lambda, the protection fraction alpha, and the rates gamma and mu. The endemic equilibrium E sub E has all four compartments at positive values. The expressions are more involved. You can see they depend on the total population M, the transmission parameters, and crucially, on the protection effectiveness bar theta. What matters is that this equilibrium exists and is biologically meaningful only when R0 exceeds 1. Before analyzing stability or designing a numerical scheme, we must ensure that the continuous model is well posed in a biological sense. Theorem 1 establishes positivity. If all initial conditions are non-negative, then the solution remains strictly positive for all times. The proof uses a comparison principle from Chirivillacid and Chirivillacid of 2010. And this guarantees that we will never have a negative populations, a basic requirement in a biological sense. Theorem 2 establishes boundedness by integrating the sum of all four equations over the spatial domain, applying Green's formula with Neumann boundary condition. we obtain an inequality for the total population. A Grunwald type argument then shows that the total population is bounded above by the maximum of initial value and lambda over mu times the domain size. This ensures no compartment can grow without bound. Now we analyze how diffusion affects stability. We linearize the system around each equilibrium point with a small perturbation of the form exponential in space and time. This gives us an eigenvalue problem involving the Jacobian matrix minus kappa squares times the diagonal matrix of diffusion coefficients. The equilibrium is locally stable when the real part of all eigenvalues are negative for every wave number kappa. The stability region is the set of parameter values where this condition holds. The key findings for the eigenvalue analysis is that increasing diffusion coefficients, we have a wider stability region. Increasing mu or delta, we have again a wider stability region. And increasing the wave number kappa, we have still a wider stability region. The figures show some of the key findings. When we increase the diffusion coefficient from this value to this value, the stability region expands. The same effect is observed when we increase the death rate mu from this value to this value. Also the stability region expands. Physically, this makes sense. Higher diffusion smooths out spatial heterogeneities, and higher removal rates reduce the infection population, both contributing to stability. To compute approximate solution of the reaction diffusion system, we develop an implicit finite difference scheme. Here Rk is equal to decay times tau over h squared, where tau is the time step and h is the spatial step. Each equation has the same tridiagonal structure. The unknown at the next time level, n plus 1, appear at three adjacent spatial nodes, I minus 1, I, and I plus 1. While the right-hand side uses the known values from the current level n. The tridiagonal structure is very convenient computational. Each system can be solved in linear time using the Thomas algorithm, making the overall scheme efficient even for fine discretizations. The implicit nature of the scheme is deliberate. It allows us to achieve unconditional stability, which means we are not restricted by a CFL type condition linking tau and h. We prove three fundamental properties of the scheme. On the left, stability. Using von Neumann analysis, we substitute Fourier models into the linearized scheme and compute the amplification factor. For the protected class, this expression is this one, and is strictly less than 1 for any positive tau and h. Hence, the scheme is unconditionally stable, and the same holds for all four equations. In the center consistency, via Taylor series expansion of all discrete terms, we show that the local truncation error is of order h squared plus tau, so as both the spatial and temporal steps tend to 0, the scheme converges to the continuous equation. On the right, positivity. The coefficient matrices B, D, K, and M matrices, they have positive diagonal entries. non-positive of diagonal entries, and are strictly diagonal dominant. Their inverses are therefore non-negative, which guarantees that if the solution is positive at time left n, it remains positive at level n plus 1. By induction, positivity is preserved for all time. Together, all these three properties ensure that the numerical scheme faithfully reproduces the qualitative behavior of the continuous model. Let us now look at the numerical result. In the first example, we set the parameters to produce an endemic scenario with R0 equal to this value. The diffusion coefficients are set to this value. The four 3D surface plots together with the 2D profiles show the spatial temporal evolution of each compartment. The protected class decreases over time. This is expected because individuals lose their protection at the rate gamma and move into the susceptible class. The susceptible class population evolves and stabilizes around a constant endemic level. The infected class also stabilizes at a positive constant level. The disease persists, and the treated class increases with time as more infected individuals receive treatment. All solutions remain positive through the simulation, and the surfaces are smooth and stable. No oscillation, no negative values. This confirms that the scheme preserves the essential properties of the continuous model even in the endemic regime. In the second example, we adjust the parameters, increasing the treatment rate beta to 5 and the recruitment lambda to 10, bringing R0 to this value, well below 1. The results are strikingly different. The protected and susceptible populations grow and stabilize at their disease-free equilibrium values. More importantly, both the infected and the treated classes decay to 0. The disease is eradicated. Again, all solutions remain positive and bounded, and the surfaces are smooth. The contrast between this figure and the previous one powerfully illustrates the role of R0 as a threshold. Above 1, the disease persists. Below 1, it vanishes. These numerical results are in complete agreement with all our analytical findings. Let me summarize our findings. A reaction diffusion SIPT model for typhoid fever was developed incorporating a spatial spread via diffusion. Positivity and boundedness of the continuous model were rigorously proved. Stability regions were characterized. Higher diffusion and mortality rates enlarge stability. The proposed implicit finite difference scheme is unconditional stable, consistent of the order h squared plus tau, and positive preserving. Numerical simulation fully validate all analytical results for both equilibria. In the future work, we consider to incorporate asymptomatic carriers and warning immunity. Formulate an optimal control problem using the Pontryagin principle for vaccination and sanitation, and extend to two-dimensional spatial domains with real geographic data. These are the references. And with With that, I would like to thank you for your attention, and I am happy to take any questions.